Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide another example of circular motion problems. So what we're looking at, whoops, get my pen on here. So we're looking at this car and it's traveling over this hill type of area, and what we're going to do here is try to calculate the maximum speed that this car can have at that position and not come off the ground. So if we start with the free body of the car, right, we've got the gravitational force down as usual, and I usually label that mg. Tires are in contact with the road. Now, even though there's 4 tires, it's pretty common to call that one force. Call that a normal force up. And if we ignore air drag, that's pretty well it. All right, so now we write a Newton's second law equation for the car. So I'll go ahead and do that down here. The sum of all forces equals ma for the car. Now remember Captain Rod's rules of thumb here. Identify the acceleration direction and call that positive. So at the instant shown, the car is traveling along a circular path. And the center of curvature of that path is down here. So the car's acceleration vector points down. And that's an example of, again, what's called a centripetal acceleration. And it has a magnitude of v squared over r. So when we write this equation, what we'll do is we'll call down positive. So that's going to be mg minus the normal equals mv squared over r. Now, this equation is good pretty well for all speeds here. And what you have to realize is the faster the person is pushing the car, if you will, meaning that the faster the car is moving, the less and less and less that normal is going to be. Because that car is going to have a tendency basically to turn into a projectile type of problem. So at the instant the car goes off the road, the normal goes to 0. And now we have mg equals mv squared over r, and the masses divide out, so we get v squared equals r times g. And I'll go ahead and calculate a value here. And I get 14 meters per second. So right at 14 meters per second, this normal force is going to 0 and the car is starting to come off the road. All right, let me read the second question here. Assume the driver maintains that speed. Find the force applied by the seat onto the driver on the picture on the right. So that's talking about this location. Okay, so now what we're going to do is we're going to draw a picture of the driver. Presumably looks something like this. And now we're going to draw a free body diagram. Gravitational force down. Now keep in mind that this mass is the driver, not the car. The seat effectively is going to be pushing up on the driver. It doesn't say anything about horizontal forces or horizontal accelerations, so we're going to leave those off. There's really no reason to put any sort of horizontal forces. And now what you need to realize about this problem is that the driver is accelerating towards here, the center of curvature. So what we'll do is we'll write a Newton's second law equation for the driver with up positive. Sum of all forces equals ma, up positive because that's the acceleration direction. So we look at our free body, and we get the normal minus mg equals, all right, ma. Here's where we have to realize that that acceleration is a centripetal acceleration, so it has a magnitude of v squared over r. So it's pretty easy math to show that the normal is going to equal mg plus mv squared over r. And now what I'll do is just going to scroll up here to take a look at that mass again. Let's see. 80 kilograms and 14 meters per second for our speed. and I get 1,568 newtons in this direction. Using 80 for the mass, 9.8 meter per second for the gravitational acceleration, 14 meter per second for the speed, and 20 meters I grabbed out of the picture. Oops. And that's it. So that should give us a decent example of how to draw free body diagrams and apply Newton's second law in these two-dimensional circular motion problems. I hope that this has helped you out. Have a great day.